So welcome to the IAMAS ECS webinar series number 10. Today, our speaker is Professor Bi Lei from Zhejiang University. Professor Bi is a talented young scientist specializing in atmospheric radiation, especially the electromagnetic wave scattering by non-spherical and inhomogeneous particles. With applications in atmospheric remote sensing, weather, and climate studies. He has received the Elsewhere Richard Goody Award for Atmospheric Radiation and Remote Sensing and the IAMAS Early Career Scientist Award. He has also been a commissioner of the IAMAS International Radiation Commission. Today, Professor Bi is going to talk about from particle optics to remote sensing, weather and climate studies, physical models, computational electrodynamics, and machine learning. So let's welcome Professor Bi.
Thank you. Dear colleagues, good evening, good morning. First, I would like to thank Professor Li for inviting me to give a talk. Thanks for this wonderful platform for young research scientists where we can share our recent research progress in this global pandemic hard time. I also highly appreciate your time for attending this webinar because the time may be too early or too late for you. So in this presentation, I'm going to review our research progress on particle optics and some application examples in remote sensing, weather, and climate studies. Actually, this talk can't be made without contributions from my postdoc and graduate students. So before my talk, a little bit of details about our university. Zhejiang University was founded in 1897, and the discipline of atmospheric sciences was founded in 1936. Actually, it is about close to 90 years old. So we are recruiting a global research scientist. So if you feel free to contact me. Where is our university? Actually, we are at a very beautiful city, Hangzhou in China. So I copied a few pictures on the website, and a few sentences here. So this is the most graceful and splendid city of the world, and one of 52 most desirable places to go. Sorry about some time before my presentation. And for my research, so there are a few parts. The first part, so I'm going to talk about what particle optics. We have interest about particle optics in atmospheric sciences. So why this topic is very challenging, and we are going to talk about computational electromagnetics, particle models, and database development, and some recent research about machine learning. And then in the second part, so I'm going to talk about some examples that we made, so in remote sensing, weather, and climate studies. Actually, particle optics is one research direction in atmospheric radiation. So atmosphere is composed of gases and particles. Particles, we have aerosols and clouds. So all these things, we term it as chemical field. So what are there in the atmosphere? Actually, what we can see and what the instrument measure is the radiation field. And in most cases, we care about meteorological field, not the radiation field. So all these fields interact, very complicated in the atmosphere. In remote sensing and weather and climate studies, actually, we want to get information about the chemical field and the meteorological field, for example, temperature, wind, precipitation. Get this information from the radiation field. So this is belongs to remote sensing studies. In all weather and climate studies, we have to deal with the interaction between them, from a chemical field to radiation field and to meteorological field. And the meteorological field change will impact the radiation field and chemical field. So there are a lot of parameterizations and equations in weather and climate models. So that's why we have interest in radiation research. And the most fundamental physical process is the light scattering. So we term it as particle optics here. So it determines the radiation field in atmosphere. The most important equation is the Maxwell equation. Although so this is clear, but if we want to get the numbers from equations, we found it is very difficult. For example, most particles in the atmosphere are non-spherical aerosols and ice crystals. Actually, this is a very challenging research subject. So when we come to deal with the particle geometry and inhomogeneity, I would like to cite one paragraph from this book, Light Scattered by Small Particles, but also is Van der Heest, a very famous scientist. And this book, we think it is a Bible of light scattering, so in our research community. So in the preface, we can see the scattering of electromagnetic waves by a homogeneous sphere is a problem with a Lewis solution. I first met this problem when I needed some numbers and curves in the astrophysical investigation. I soon learned it is a long way from the formula containing a solution to reliable numbers and curves. So in this book, most research is about a sphere. So when it comes to non-spherical particles, so the problem is more challenging. But in application perspective, particle optics is very important. So it is an input to radio transfer. So with application to remote sensing, with application to satellite data assimilation. So if we input to the mass scale meteorological model, and then we can do some weather analysis and input simulation model, and we can study climate prediction and some assessments. So this is a kind of flowchart from fundamentals to applications. So now we come to the computational electromagnetics. So for all things have to start from the most simplest problem. For example, light scattered by one particle. Okay, so with the incident field and the scattered field, we have the definition of amplitude scan matrix. So this amplitude scan matrix depends on particle shape, particle refraction index, and particle size. So if we have the amplitude scan matrix, we get all the information about light scattering, for example, optical properties. So incident field, we have Stokes parameter. It describes the polarized state of electromagnetic wave. And the scan matrix combines the incident wave and the scattered wave. And also other quantities are very important in radio transfer. For example, extinction efficiency, single scan albedo, symmetry factor. So for all arbitrarily shaped particle, arbitrary refraction index, arbitrary particle size, we want to get these kind of optical properties. So we have to develop tools. So this is a Chinese saying. So if a craftsman wants to do good work, he must first sharpen his tools. We have spent a long time working on this research subject. Just like Van der Heest wrote some sentences in his book. So it is a long way from the equations to get the numbers. So we have spent a long time working on this issue and developed many methods. For example, invariant embedding matrix, physical geometric optical hybrid, double series, complex angular momentum. I'm not going to talk about the details about these techniques. So if you have interest, so so we can share our publications. So some other publications I still very enjoy the times when I was at Texas A&M. So some work was done in this very top building at Texas A&M University, and Professor George Cardwell and Professor Ping Yang are my advisors. So I learned a lot from them. One method I want to highlight is the invariant embedding matrix method. I think this is a breakthrough work. So in secondary computation, for every particle along fractal geometry, we can assume it is a homogeneous sphere, for example, and then discretize the homogeneous sphere into multiple layers. And then we can compute some kind of T matrix. I didn't give the definition of T matrix. So if we know the T matrix, we can get everything about light scattering. And then it is easy to get the T matrix of an inscribed sphere. And then step by step, we can get the T matrix of these non-spherical particles. So this is invariant embedding principle. And the T matrix has some wonderful features. So first, it is about flexibility. We can deal with arbitrarily shaped and homogeneous particles. And second one is the accuracy and efficiency. This is because we implemented analytical random orientation average algorithm. And the third one is the applicability. So the particle size parameter can be up to geometric optical domains. And we can deal with a wide size parameters of particles. And we made some recent progress in the T matrix methods. We developed a GPU version, and this technique was recently published in Frontiers in Remote Sensing. We found that the computational speed increases by 10 to 20 times. So this is very nice. And then with the computational methods, with tools, the second thing we have to deal with the particle models. So actually, the particles are very complicated atmosphere. So you can't find a well-defined particle geometry, even for the ice crystals. And the aerosol particle shapes are even more complex. So we are thinking about, can we develop a comprehensive particle geometry model to model these particles? We can't define the details of particle geometries. And then we come to an idea about the superspheroid model. Actually, a sphere model is commonly used. And then people try to use the spheroid model to improve the sphere model. And with the advance of the computational techniques, and then we think about superspheroid, it has one more degree of freedom. So this diagram shows the particle geometry space. The horizontal axis is the aspect ratio. The vertical axis is the roundness parameter. With different roundness parameter and aspect ratios, we can have quite different particle geometries. And the sphere and the spheroid are special cases. That means we have more particle geometries by using this model. And why we want to have some more freedom? So this is a very interesting paper. In this paper, the authors try to find an equation to draw an elephant with 4 complex parameters. But if you want to have a wiggling trunk, for example, like this, you have to increase the freedom of the equations with more variables. So why we want to increase the freedom? With the increase of particle geometry freedom, so we expect to have some optical equivalence between model particles and the realistic particles. So this figure compares the optical properties, including scattering matrix, extinction efficiency, asymmetry factor, and compare the optical property to quite different particle geometries. Actually, they are very close. So this optical equivalence is very, I think is very important if you want to apply this model in applications. And then we try to model the optical properties or realistic dust. So this is a secondary matrix measurement. The dot points here. And all the colored curves are from the simulations. Different colors have different model geometries. For example, the blue curve is for spheroid particles. With different rounded parameters that we have different superspheroids. Actually, we can find when the particle rounded parameter is larger than 2.6, so the simulations are very close to measurements. That means this is a very good model parameters to represent dust in real atmosphere. And then we try to compare the depolarization ratio and the LiDAR ratio of dust. These ratios are very important in active LiDAR remote sensing applications. So we compare simulations and modeling measurements. So these dot points are from the HSRL at 355 nanometer from NASA. And all the curves are from all the particle geometries, all the particle shapes, all the particle sizes. And we find that the measurements can be well covered by these modeling simulations. So this is also very nice. And then we look at the Aerosol observations. So Aerosol is a French satellite. So it measures polarized radiance. And then we compared the polarized radiance from measurements, real dust events, and the modeling simulations from the vector radius transfer equations. So here, the dots are from the simulations, and the colored area is from the measurements. We found that with this kind of superspheroid geometries, we can also reproduce the polarized radiance observations. So we are very excited about this result. And then my colleague asked me a question: can you use a superspheroid model to represent realistic ice crystals? Actually, previously we tried to define ice crystal models use some realistic particle geometries. And then we tried to, can we apply this superspheroid model to represent ice crystal, and did some comparisons. For example, this is the comparisons about the drugstore geometry and the superspheroid. And we found that the optical properties are very close. If we have the same shape index, we define the shape index here. We also made some simulation about the complex aggregate particles, and the comparison is also very encouraging. So we are confident about develop a database for superspheroid and then apply the database in applications. And then we did a number of simulations about the particle geometries, for example, aspect ratio, roundness parameters, refraction indexes, including the real part and the imaginary part, and the side parameters and the secondary angles. With all these parameters, we found that the database is huge. For example, for this database, is about 127 gigabytes. I found it is very difficult to share and apply in models. And then we have an idea how to use deep learning approach to compress the database. This idea is, for example, we can use this database as a training data set, and then use the DNN model, and then predict the extinction efficiency, single-scan albedo, asymmetry factor, and phasometric elements. We found that if we increase the network parameters, so the accuracy will increase. So this is R-square determination coefficient. So the higher this coefficient, that means the better accuracy. And the root mean square error will decrease. We found somewhere, so we have an optimal number of network parameters at the accuracy. And we found that the database can be compressed about 6,800 compression ratio. And we are also very excited about this feature. And this is a comparison between prediction values and the database, and the accuracy looks very good. And then we specifically look at the comparison between attention efficiency, single-cell albedo, asymmetry factor, and the scanning matrix. And the true value and the predicted value are very close. Also, all these are homogeneous particles. In real atmosphere, actually, particles could be inhomogeneous. For example, this kind of a core-shell structure. So internal part, for example, dust, it is irregular and non-spherical. And then we have some liquid aerosols forming a shell. And then we build a comprehensive data set by including the particle inhomogeneity here. And also use kind of residual networks, try to compress and predict the optical properties of large size parameters. So after that, we can have many data about the particle optical properties. We are thinking about the applications in remote sensing, weather, and climate studies. So here we list some application examples because we only have 30 minutes of time, so just a few examples to show applicability of a superspheroid model. The first one is the dust aerosols. We have special interest about the dust composition identification. So here we look at the thermal infrared band. So this is from the CRIS satellite observations. So in the atmosphere window band, if we have a dust, we have the kind of elective slope. So this is a signal about dust. But if you observe the cloud, it has a positive slope. So this is a general features, slope features. This is an indication of dust and the cloud. But we want to look at the composition of dust. This is the difference between simulated and observed Bradley temperature. We observe some peaks. All these peaks actually is closely related to the some minerals, for example, quartz and calcite. Because for these minerals, we have special absorption band. Okay, for example, quartz have the is to band absorption, and this is for the kaolinite, and this is for calcite. So if we can retrieve the peaks of this, we can obtain the information of dust composition. And we did a lot of simulation runs, and we found that calcite is quite common, so in the Asian dust and also Africa dust. But the kaolinite, the content is high in Africa. And we also try to retrieve the mineral dust information from the geostationary satellite, for example, phone-in-4A gears observations, and did some, we have some preliminary results, and also it's kind of exciting. For example, so this kind of green, blue curve, blue dots are from the satellite retrievers, and all other data are from the literature about the composition content. So they're quite consistent. So we hope we can apply this technique to do some global retrievals and so in future. So this kind of remote sensing application is thermal infrared band. And then we also have interest about the hematite composition in dust. We have interest about this because so the dust has absorption at the short wave band. So this is closely related to the hematite content. And we also want to study what's the impact of dust absorption in a global circulation model, because dust absorption impact the single scale albedo very much. And we also use the superspheroid dust particle models. And here is just one example. So we collaborate with a few professors, for example, Professor Yi from the Zhongshan University. And this paper was published in Geophysical Research Letters. And the thing we found is that, so in China, there is a May rain bed. So the time is about in June. And we found that the absorption of dust can inhibit convective May precipitation here. So this is quite an interesting feature. The second thing I want to share is about sea salt aerosols. Sea salt aerosol is one important aerosol type in the atmosphere. It comes from the sea surface, from the bubble bursting. So we have some more particles get into the atmosphere. If we look at the image of the sea salt aerosols, so if the relative humidity is low, the particle is dry, kind of non-spherical particles. If we have a higher relative humidity, the particle can be inhomogeneous. And for very high relative humidity, the particle is homogeneous particles. We think that the non-sphericity and inhomogeneity will have impact on optical properties. And then we did some simulations and compared with the observations. So the left panel shows a comparison about the depolarization ratio of a cube and a coated cube and a rounded cube here. We found that, for example, for high relative humidity, the depolarization ratio is very small, the kind of this particle. But if for non-spherical particle, so the depolarization ratio is obvious. But for coated non-spherical particles, the depolarization ratio will increase. And then we look at the observation data. So this the left axis, this is the relative humidity, and the yellow one is the depolarization ratio. And we found that depolarization ratio is correlated with the humidity. Also, this is also very interesting. And we also did some simulations and compare with the Aerosol observations. And the thing we have interested here is the near backscattering polarization radiance. From the observations, we have some raw data. But if we use a sphere model to model sea salt, so actually these black dots, it is very difficult to get this negative branch of polar radiance. But if we include the inhomogeneous sea salt, the modeling simulations will closely match the Aerosol observations. That means if the inhomogeneous effect should be included in polarized sensing. And then we look at some a very interesting thing about the tropical cyclones. So if the inhomogeneity of sea salt aerosol affect the prediction of landfalling of tropical cyclones, so this actually collaborate with a lot of professors in our university, Dr. Shu's group. We look at the example of Typhoon Fatal in, so this is a typhoon, so significantly people have done research about this typhoon. And we look at the precipitation. So this diagram is about the observation of the precipitation, and all other panels are from the WRF modeling simulations. So here we didn't include the sea salt, but here we include the homogeneous sea salt. Here we include inhomogeneous sea salt. We found that the inhomogeneity of sea salt will suppress the rainfall, and then the data will be closer to the observations. So if you have interest, there are many details in the paper. We also did some global simulations about the climate radiative effect of sea salt. Actually, the inhomogeneity depends on relative humidity. So it is not surprising that the relative difference of radiative effect is large. So in the coastal regions. So okay, so this is about another example about the sea salt aerosols. But aerosols are complex. So we developed a new intermixed aerosol optical scheme and then implemented it in the Wolfram models. So in this scheme, we consider dust, organic carbon, water, sea salt, sulfate, nitrite, black carbon. And then for these aerosols, we consider as a share, but for dust and black carbon, we consider to be an integral core. And then we did some parameterizations, and we can get some aerosol optical properties. Here, we also use the neural network to parameterize the optical properties. So here are some modeling assessments. So the first column is the homogeneous particle models. The middle column is inhomogeneous particle models. In the third column, we include the non-spherical geometry in the models. The first rule is the AOD, and the second one is the absorption AOD, and this is the symmetry factor. We found that there are some many differences about optical properties, and then we assess the impact of the optical difference on the temperature perturbation. So this diagram is a Sichuan Basin area. We found that we include the aerosols, so the temperature we have a large difference. So this is the North China and this is the Taiwan Basin. And then we specifically discussed the non-sphericity effect and inhomogeneity effect on the temperature. I'm not going to talk about details, but I want to say that the particle geometry and homogeneity have opposite impact on temperature bias. And this is very important in the boundary layer. And these are examples I want to share today. And here I want to try to summarize my talk today. This is also the paragraph from the Van Hoos book. So I soon learned it is a long way from the formula containing the solution to reliable numbers and curves. Actually, my involvement in this journey is also very long. So to summarize, I want to just say that it is fun to play particle optics, and there is no end. So that's all for my talk today. Thank you very much.
Okay, thank you very much, Professor Bi for sharing this wonderful talk. So we have some time for a few questions, and please ask your question in English because we are going to post the video of this talk on our on the IAMAS YouTube channel. So, does anyone have questions? So, we have a question here. So we just wonder if you have a database for aerosols with different shapes and different mixing states, like a database for the single scattering orbital and a symmetry parameter, like that, so that can be used easily for remote sensing applications.
Yes, so we have a lot of data. So we try to organize this data and then share in the light secondary research community. But now, so we have published some papers use this data, but we need to organize and try to share so this database with details about the data description. So in future.
Yeah, that would be very helpful for remote sensing and also for climate, like aerosol radiative forcing research.
Yes.
Yeah. And the other question is, you mentioned the effect of inhomogeneous sea salt, right? So it can suppress rainfall, like reduce the cyclone strength. Yeah,
Yes.
yeah.
Mm.
So does that mean there are something different in the hygroscopicity or in the cloud microphysics caused by the inhomogeneous sea salt? I just wonder what is the mechanism.
Yes, this is a very good question. So actually, for a landfalling typhoon, so some areas relative humidity is low. And when the relative humidity is low, the sea salt particle could be homogeneous. But this feature hasn't been considered in models. So in this work, we just try to change the particle properties and include the particle homogeneity in the relative humidity range, for example, 50% to 70%, and then try to compare the simulations with different modeling setup. And then we found that it could suppress the precipitation. So here is a diagram to show why it will suppress the rainfall. Actually, the cooling effect of inhomogeneous sea salt aerosols. So if we include the homogeneity, we have more cooling effect. And then we found that this cooling effect will cause a stable layer. So from 850 to 700 the pressure. So this will result in a downdraft and a divergence in the low atmosphere, and then finally reduce the rainfall. So if you have interest, I can send you this paper. Actually,
Yeah.
this is done so in Dr. Schu's group. So I think this is very interesting.
Yeah. So yeah, it was a bit different from what I thought. And so inhomogeneous sea salt has more cooling. What's the reason that it has more cooling? Because it's still scattering, right? And this shouldn't depend on the phase function. It just depends.
Actually, for homogeneous particles and the inhomogeneous particles, the assembly factor has a huge difference.
Yeah,
Assembly
yeah.
factor has
I
a
was
huge
just
difference. Mm.
right.
Mm.
Uh, Yeah, so I'm just asking why does the asymmetry parameter, so you mean the cooling is the surface cooling or the atmosphere cooling, is the atmosphere cooling at the level of sea salt?
Yeah, because the asymmetry factor is different. The short wave, so the forward short wave and backward short wave balance is different.
Mm, okay,
So
thanks. Yeah,
I know I
that's
forgot the more details about this research. Probably know we can. I will send you the paper. Mm.
okay. Yeah, that would be great. So it's very interesting to learn that the non-spherical and the inhomogeneous particles will have very different or sometimes totally reversed effect. It seems there are a lot of work in climate models and remote sensing to do. Yeah.
Yeah, yeah.
Um, yeah. So I wonder if any of our audience have any questions.
Hi, Jing. May I ask some questions?
Yeah, sure.
Okay, the first question is also related to the TC development. So I wonder, so when there are a lot of sea salt aerosols, I see that the location is the cloud band, where the cloud band lies. So the cloud is so deep. So how could the sea salt affect the solar radiation too much? Maybe the effect should be low in my expectation. So this is the first question. The second one is, I wonder, you know, the dust aerosols by the radiative effect could change the development of clouds. So I wonder if the optical properties, just like the homogeneous and the heterogeneous you introduced here, how big this effect could influence the development of clouds?
Yes, this is also a very good question. Actually, in this study, we just concentrate on sea-salt particles. We didn't look at the dust particles and the radiative impact and other TC development. About the inhomogeneity here.
For me, the second question is not related to TC. The first one is. The second one is for general.
Okay. Actually, just if we look at the simulations, we look at some difference here. And just imagine why there are some difference. We look at I remember we look at the sea-salt loading data, and also the relative humidity distributions. So where the relative humidity is low, where the relative humidity is high. So this is important to understand the radiative impact. I can't answer you this question in more detail here. Okay, but I will send you the paper. So
okay,
this is,
I will read the paper. I just wonder. It seems to me this is the location with clouds there. Maybe the cloud is very deep there. Okay, thank you.
Thank you.
Okay, so because of time limit, I think we have to finish here today. Let's thank Professor Bilei again for his wonderful talk. And good night, everyone. Thank you for your attention.
Thank you very much. Thank you, Professor Li.
Yeah, thank you.